I want to talk about, causality and the Markovian property. Okay, so what do I mean by that? So our initial time, we chose at t prime, right? This was our initial time. And our final time was t. I'm just establishing the notation, because I'm not very consistent with notation from lecture to lecture or course to course, so it's a good idea to establish the notation. So then the time evolution operator is ut comma t prime, or if the Hamiltonian is time independent, then it's u t minus t prime. Okay. So now, causality demands that, if we evolve our system from t prime to, say, t, but we can always evolve it to an intermediate time, say t double prime, and then evolve it to t. So, the two should, the two, evolving it first from t prime to t double prime and then t double prime to t prime should be the same thing as evolving it from t prime to t. So that means that on physical grounds, we expect our propagator or our time evolution operator to have this property. Right, where t double prime is a time which is greater than t prime, but less than t. Do you agree? It's pretty obvious, right?
Yes, sir.
So this property is called the Markovian property, okay? So this is the simple, sensible property is called the Markovian property. So what it's saying is that, the state of the system at time, say t, only depends on, say, t double prime, the previous state. So suppose that this was a discrete step. We can think of it as there could be some system which is a discrete system where, the time steps are discrete. Although I have not drawn them in to be equal, but, just ignore that. So if this was such a system, then, suppose that the state of the system depends on the time right before. And the state of that system depends on the time right before. That is the Markovian property. If the state at time t depended both on the state of both t double prime and t prime, then the system would not be Markovian, okay? So this is just Markovian. Now, the Markovian property, it has a lot of mileage. Now, what I want to show is that I want to explore this simple Markovian, equation in terms of the propagator in coordinate representation, which we call k. Okay, but before we do that, we can, in principle, if you are given a time interval from, say, t to t prime to, say, t, we can divide up the time interval in as many pieces as we want, right? So this could be, say, t1, t2, t3, t4, t5, dot, 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 tn minus 1. And this is tn, but we write it as t. And this is t0, we write it as c prime. And, we should be able to say that u of, say, t prime is the same thing as u tn minus 1, u tn minus 1, tn minus 2, dot, 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 u, say t1, t prime, right? Does that make sense?
Yes, sir.
Yeah. So let's explore this very seemingly simple looking relationship in the language of the the position dependent propagator. So the position dependent propagator, if you remember, we defined it as xt and x prime, t prime in one dimension. And in the tutorial, you're asked to find the exact form of this guy for the free particle. We won't need that here. But that guy, we defined it as 1/2 pi h bar, and then integral over some momentum u of t comma t prime e to the power I px minus x prime over h bar. Right? Do you remember that? So I think that's part of part 2 of your tutorial. But let me just remind you where it came from, and it'll make sense. It comes from the fact that if I express my state at some time t as a, in terms of the state at an earlier time, say x prime, t prime, and then the object that propagates my state at that earlier time is x of t, x prime, t prime, right? So this is how we defined k. And if I compare k, this definition, with the definition of u, which is simply u of t, t prime, acting on psi of t prime, and there's an x dependence that is equal to u of t of x. And the way we think of this equation is as follows. We think of this equation as, suppose this is my earlier time, t prime, and this is my space in my later time, t. So this is the x-axis, let's call it x prime axis, and this is the x-axis at time t. And what we are interested in is we are interested in finding what our system looks like, the wave function of our system, psi, say at this point, x, at time t. And what we expect is that, well, it should depend on the state of the system at time t prime, but it should depend on all values of x prime, right? Because, for example, because we are dealing with wave mechanics, so waves can travel from there to here. It can travel from here to here. And it can travel from here to here, right? And the effect of the wave, say from this point to this point, so let's call this point say x prime. Sorry, I'm using the same symbol. So the effect of this point on this point is what we are calling k x prime t prime. Sorry, it should be the other way around. K x of t x prime t prime, right? And of course, since we expect this guy to depend on the value of the wave function at all point in space, but how does that value of the initial value of the wave function propagate in time is captured by this thing, okay? So in that sense, this thing is equivalent to this, and the equivalence is provided through this equation. I think I did provide you with this equation in the previous class, right?
Yeah, I remember it.
Yeah. So, so as long as, this kind of makes sense, roughly, you should be in good shape. Okay, so, we can think of it in the following way. We can think of it as, say, the time evolution operator, and these things we can think of as, psi p of x and psi star of p of x prime, right? The momentum eigenstates, right? This factor can be thought of like that, right? You know that, right? So, we know that those are the momentum eigenstates. So, in some sense, what you're saying is that, what we are looking at is how, the momentum eigenstates are, quote unquote, the free waves are propagating, but their propagation is determined by the time evolution operator, okay? So, there's a lot, there's a lot more to unpack from this. Another way of thinking about K is the following, is that suppose that you had your initial state, this is your final time, say t, this is your initial time, say t prime, and suppose that your initial state was a delta function. So initially you had a particle at, so I'm just drawing the wave function on the same picture, although it should be in an orthogonal plane, right? So suppose your wave function was a delta function at x prime, and you want to know what is the value of the wave function at x. Okay, so according to our formula, the wave function at x is x of t, the original wave function at x prime of t prime, and then k x t x prime t prime, d of x prime. But we know that we have assumed that the particle was localized at a position. So, by Heisenberg-Thomson principle, it should, its momentum should be completely delocalized. So it's x of t, then x prime of t prime, and then I get here delta of x, let's call this x double prime, so x minus x double prime, okay, at t equals to t prime. So if I now do the integral, what we get is that we get k x of t x double prime t prime, right? So we see that another interpretation of the propagator is that it is the wave function of a particle whose initial wave function was that of is that of a delta function. In some sense, the delta function in the sense of distributions, in the sense of functional analysis, represents like the identity, right? The unit. So what the propagator is doing is that it is telling us how, for a given system, so it'll depend on the Hamiltonian of the system, how, for a given system, a unit wave function propagates in time. Okay, so let me make a comment. So, the propagator represents how a unit wave function, I should put this in quotations, represented by a Dirac delta function, evolves over time. Okay? So, any questions? So I'm just like giving you some formal aspects of the propagator. But I would really like you to go through that tutorial to get everything out of this, out of this lecture.